The second video looks at what's called the central limit theorem. So it extends the distribution of the sample mean to other distributions that are not normal. So if the sample size is large enough, then even if the underlying distribution is not a normal distribution like we were talking about before, the distribution of the sample means is approximately normal with mean mu and standard deviation sigma over root n, or the variance being sigma squared over n. Sigma over root n is called the standard error of the mean. So in formal terms, the central limit theorem states the following: if your x1, x2 all the way up to xn is a random sample of size n from any distribution with mean mu and variance sigma squared, then for large n, the distribution of the sample mean x bar is approximately normal with x bar following the distribution that's normal with mu and sigma squared over n as the variance. This approximation improves as n gets larger, which links back to sort of GCSE if you are doing any experiment and collecting data. Your observations and your probabilities will be more reliable the larger your sample size. So as n gets larger, the approximation improves. And also the approximation is also improved if the distribution of x, whatever it is like a normal distribution. So it's symmetrical and unimodal. So the more your underlying distribution looks like the shape of a normal distribution, then the better the approximation will be. In terms of n being large, n is greater or equal to 30 is usually sufficient for a reasonable approximation. By the way, also for large n, then the sample total rather than the sample mean is also approximately normal with mean n times mu and variance n times sigma squared. So this example looks at a sample size of 100, and this sample was taken from a population of voles whose masses are believed to have a mean of 32 grams and standard deviation of 4 grams. Calculate the probability that the mean mass of the sample is A less than 32.6 grams and B lies between 31 and 33 grams. So we've got a sample size of 100, so we know n is 100. We know that our average, our mean, is likely to be 32 grams, is that what we're using, and our standard deviation is 4, so our variance is 16. So we need to find, because we're talking about the mean, the distribution. So using the central limit theorem, because we've got a large enough sample size, we know that E of m, E of our mass of voles, is 32, and that will be our mu, and our var of m is 4 squared, or 16, which is our sigma squared. So using that, m bar, which will be the mean mass of the random sample of 100 voles, means that E of m bar is 32, the same, and var of m bar will be our sigma squared, so our 16 over our 100. Okay, so 16 over 100 will be our sigma squared over n, which is 0.4 squared, or 0.16. This means that using the central limit theorem, m is approximately following the normal distribution with mean of 32 and variance of 0.4 squared. So now all you need to do is look at the questions, and using your calculator and the normal distribution setting, then you just put in the information about the mean and the variance. We want less than 32.6, so 32.6 is our upper limit, and our lower limit is a very large negative number, and that will give you on the calculator 0.933. And then for part B, if you enter the same information for mu and sigma squared, then we've got a lower limit of 31 and an upper limit of 33, and we get 0.988.